So we are now in our last set of notes for the course. I originally did consider actually removing this last set of notes from content, but I really thought it was still important for you to see another generalized linear model so that you didn't think logistic regression was the only kind of GLM out there. So we're going to do an introductory look at what's called Poisson regression. Now some of you may have heard of the Poisson distribution before, but that's not something that you're expected to know coming into the course. So kind of a quick idea of why Poisson regression would want to be done is let's first go back and think about logistic regression. The goal of logistic regression was to model a binary response variable where we had just a success or failure in data. Poisson regression is no longer looking at trying to model this binary response variable, and instead is trying to model counts. So counts is something that can come in a contingency table, and so you might be trying to model the counts, which does have to be a non-negative integer. One of the biggest ways we can model this is through what's called the Poisson distribution, and Poisson models the number of successes or kind of occurrences during a certain time frame. And so the Poisson regression is what's going to be done here. Just as with logistic regression, we could look at having multiple explanatory variables, but again, since we're just doing an introductory look at Poisson regression, we'll just talk about using one explanatory variable here. So let's talk through the components of a generalized linear model and talk about how it pertains to Poisson regression. Well, the three components of any GLM is the random component, the systematic component, and then the link function itself. Now I'm actually going to do the systematic component first because it's the same as it was before. It is just going to be this alpha plus beta times x. And alpha again kind of serves as like our intercept that we're working with, and beta would serve as a slope-like measure. And again, I say slope-like measure because of these other two components. It may no longer be a linear regression that we're talking about here. Now the random component comes from sort of the distribution we believe our response variable is being modeled by. And here we believe we're going to be using this Poisson distribution. Now the Poisson distribution has one parameter that they work with, and that is actually mu, which is the population mean. For those that would like a quick review of Poisson that have seen it before, you may remember that for the Poisson distribution, if you wanted to find the probability that y equaled y, that would be e to the negative mu times mu to the y over y factorial. And y could only take on positive whole number values and did not have an upper limit to what it could take on here. Now you might have used a slightly different looking letter here. For example, you might have used the Greek letter lambda instead of mu, but since it really is the mean, that's why I'm preferring to use the mu here instead. The last thing we need for a generalized linear model is to understand how we're going to link the random and systematic component together. So the most common link function used here is actually the log, or the technically again natural log link function. So we would say that the log of the mean is what our alpha plus beta x would be, which then if I wanted to solve this for mu would then tell me that mu would just be e to the alpha plus beta times x. Now a question that some people might ask is, why would we actually use the log or this natural log link function over the identity link function? So first, what do I mean by identity link function? There instead we would have just said, well, that mu would be equal to alpha plus beta times x. Or if you prefer me to write it this way, this would be our expected value of y, which is equal to the population mean. And this is actually what it looks like for regular linear regression. We use this identity link function. So why might we want to actually use the natural log link function here. Well, one thing that this ensures here for me is if I take e raised to any power, I cannot get a negative number. And knowing that I'm working with count data, it cannot have negative numbers. So if I use the log link function, only allows for non-negative values. So it will not allow for any negative values to happen when I use this function instead. This one would allow for negative numbers to happen. This one will ensure that we never get a negative number. Now, thinking ahead, since we're going to just be using a sample of data to make our decision, keep in mind that what we're really going to have here is we're going to have a mu hat function that's going to be e to our alpha hat plus beta hat times x. When we actually use a sample to estimate it, we're going to have those hats on all of our Greek letters there. So let's talk through a couple ideas of when x and y here might be working with this Poisson regression. So let's suppose that y might be the number of credit cards that someone has. And maybe a possible x value that I would use to predict that might be someone's income. Another example, maybe let y be the number of cars that go through a certain intersection. And x might be the number of businesses within a 1 mile radius. That might help me predict that. I mean, x could maybe be like the population within 1 mile. Like there's different things I could use, of course, as my explanatory variable here. For another one, maybe let y be the number of arrests in a city during a week. So then maybe a good explanatory variable there might be looking at the population size of that city. And I cannot spell today. There we go. Those are some examples of when we might use Poisson regression. In our next video, we'll go ahead and pick up with an example.